Okay, it's time for you, Professor Yang.
Okay. Hello, everyone. Thank you for joining Photon Research Spotlight webinar. This webinar program was created to highlight and showcase research work that was published in Photon Research. And every month we select one papers and share with that with the general public. But before I introduce today's speaker, let me give you a brief introduction of the journal which sponsors the program. So Photon Research is a relatively young journal. It was founded in around 11 years ago, and this journal actually have very good editorial board, who work as a gatekeeper to ensure only high quality papers that meet the criteria of the journal can be published. And here, for all the papers that submitted for Photon Journal, they will go through the editorial review process first. Yuri, Yuel, and I oversee this process. Only the papers, the research that fall in the scope of the journal can pass through this process. Then it will go through the standard external review process, and the decision is made by the comments we collected from the experts in the field. And based on the journal citation report this year, Photon Research is ranked number 12. So citation, I would say impact factor is not everything, but it is a reference you might consider when you choose a journal for your papers. When I say citation, I would say it's not a only factor to decide the journal, but it can be a reference to tell you the visibility of papers published in this journal. Here we select some papers published in 2022 and 23, and citation from the citation you can see here, you will see that the papers that was published in Photon Research can get sufficient visibility by the peers in the field. And every month, we of course have one paper selected for cover page. That is one way to promote research published in the journal. But in addition to that, we have some other mechanism. For example, every month, around 10% of the papers will be selected for as editor-in-chief, choice. And also, one paper will select as spotlight article. And every other month, and I think this year, we also choose one paper for press release. And so I would like to encourage you to submit your best work to Photon Research. And also in the submission process, there is a choice for you to upload very nice images that can be used as a candidate for cover page. And we do seriously consider those papers. Even if your paper is not selected for cover, we will reach out for news article to promote your research. And as I said, probably you have heard of the Photon Research Journal as a partner journal. With that, you can see that Photon Research has some benefit or advantages to enjoy the promotion by different platform. For example, Optical Chinese Laser Press and Optical Publishing Group. Both platforms will promote and showcase paper published in Photon Research. And as I mentioned before, we have very nice editorial board, really strong journal development. So they try the best to promote the journal in different conferences and workshops. And in addition to that, we also try to leverage the kind of media. For example, Chinese Laser Press has its own WeChat platform, and they have different kind of WeChat platform to serve different purpose. And we leverage on some of those. For example, we every month we do have different kind of WeChat articles published on this platform. You can see this article talking about specific papers, and there is article talking about webinars we created for interview with pioneering researchers in the field. And the most of these, this article can have more than thousands of read by the audience, by the general public. In addition to that, we also create different kind of mechanism to promote researchers in the field, because in the end of the day, research is done by researchers. So in addition to associate editors, starting from last year, we create a different kind of group of people, researchers. We call them assistant editors. They basically work with associate editors to go through the papers submitted by Photonics Research. So through that, our young people also get experience about the review process. And after a few years of experience in this role, then they can be promoted to associate editors for the journal. And then sometimes we invite them to write comments about papers we plan to promote. And those are two examples of comments written by our assistant editors. And in addition to this standard way to promote the journal, every year we chose 2 papers as Editor-in-Chief Choice Award. And there, if you ask me what is standard to choose this award, I would tell you it's not just, as I said, it's not about citation, it's about impact and innovation. And the research can come from any group. It can be theoretical work and could be experimental work. And some awards are given to a senior group, but sometimes awards are given to young group. So everybody have equal chance to be selected for this award, as long as this is a breakthrough discovery in the field. So I also want to encourage you to consider that And in addition to that, all those mechanisms I just mentioned, in 2021, we create Photonics Research webinar. This webinar was created to give us a chance to see the experience and learn about the research experience of those pioneering research in the field, because sometimes there are a lot of stories behind the research discoveries. Those kind of story, especially personal story, actually can give us a glimpse of how to grow into someone that can make a significant contribution to the field. And sometimes some of the stories are really enlightening to tell you how to find the kind of research that can contribute to the growth of the field. So, for example, in 2021, we interviewed Marlon Scully, who is a pioneering researcher in the field of quantum optics. For the first interview, it was done by me and Professor Marlon Scully. But after that, we have the mind to promote young researchers. So starting from 2022, we decided to change the format of this webinar. So instead of me, actually we invite junior researchers who have certain association with the senior researcher we want to interview with, as a person to interview the senior researcher. For example, 2022, the webinar is given by the guest of honor of the webinar is Professor John Bauer. We chose Professor Lin Chang, who is a professor in Peking University, to interview him. Lin Chang was a student from Professor John Bauer's group. And last year, the conversation is between Professor Hao Sun from Tsinghua University with his mentor, who is a professor in UC Berkeley, Professor Connie Chang. So it was a way to young researchers also give a chance to learn about the history of the field of photonics through the story of a senior researcher. And also, in addition to seeking for the candidates for this webinar, we also welcome a nomination from the community. If you believe your advisor is someone that will share a very interesting story with the community, I would like to encourage you to reach out to us. So in addition to those webinars, and this cover story and all kinds of mechanisms to promote research, we also organize a workshop every year. Every year we chose one interesting topic to share with the community, because through the workshop we will have chance to have in-person meeting with potential readers and authors in the community. And for example, in 2019, we chose optical microresonator as a topic. Now, in the past few years, probably a lot of people experience the excitement in the field. For example, frequency cone is one of the most exciting topics in the optical microcavities. In 2020, the topic is silicon photonics. That is not surprising, because for the past few years, probably you won't be overlook the rapid progress in the field of integrated photonics. And also AI, artificial intelligence, is everywhere these days, right? And you can see around 3 years ago, 2021, we already decided to choose deep learning in photonics as a topic for our workshop. So that being said, every year we carefully choose a timely topic that is of great interest to the community. And in 2023, that last year, the topic is about optical matter surface. So every year we try our best to choose a topic that of interest to the community. As I said, we are a community. The topic is just not decided by the editors themselves. Instead, we reach out to the community to get feedback from a lot of people and then decide the final topic for the workshop every year. And I would say to establish a journal with a great reputation, the contribution from the community is very important. That is reflected by the strong support from all different parties. For example, last year we have a serious event to celebrate the 10th anniversary of Photonics Research, and Tsinghua University is the first sponsor for the event. And in addition to organize a series of talks shared by the authors of Photonics Research Journal, we also organize panels, including the top tier research in the field, to share the stories and the experience in the life. And I think that kind of discussion is really helpful for the community, especially for young researchers. And in addition to Tsinghua University, University of Science Technology China is really supportive for the journal. Actually, our deputy editor, Yu Yao, is a faculty there. And our second event was organized there. And the third event to celebrate the 10th anniversary was organized and sponsored by the Sun University. And those are just a few examples to show the strong support we have got from the community. So in addition to all those, on top of those, we also organize the feature issue every year. Similar to the way we chose topic for workshop, we also solicited feedback from the community. Now you can see for every single issue, we have multiple professors. Those are normally the people who already have established a reputation on that topic. So every year the topic is carefully chosen. So it's not surprising to see those topics for feature issue actually align with the issues, the topic we chose for the workshop. So this year, the topic is about integrated photonics. So we're now looking for feedback from the community about the topic of next year. I definitely welcome the feedback from all of you. So time is short. I should definitely need to save time for speaker. And here as just 2 emails you can use to reach out to us for your feedback. If you have any comments that help us to improve the journal, please feel free to reach out to us. So now it's time to talk about our speaker. Today is my great pleasure to introduce today's speaker, Professor Kebin Shi. He's a professor at Peking University. He is a visionary leader who has made important contribution to advanced imaging and spectroscopy techniques with high spatial temporal resolution. I have known Kebin for more than, say 15 years when he was still a student at Penn State University. He is truly the kind of researcher's dedicated effort to one field and really dive deep to discover things that are beyond we can imagine. So today, through his talk, we will have a chance to delve into his work on reflective ultra-thin light sheet microscopy with isotropic 3D resolution, which will represent a significant leap forward in light sheet microscopy. So please join me in welcome Professor Kebin Shi, who will now share more insight into this remarkable advancement in microscopy.
Okay.
So, Kebin, the stage is yours.
Okay, yeah, I'm starting to share my screen. Can you see my screen?
Yes.
Okay, so so first I want to thank Professor Yang and the editorial office of Photonics Research Journal to invite me for sharing my recent work on this light sheet imaging technique. So today, actually, I probably will introduce 2 works. They are closely related. One is just Professor Yang introduced, which was published early this year in Photonics Research. Another one actually is a very close follow-up for the first work, and we're still working on this project, and the second work actually is in review, so it's pretty new. So today my topic will be majorly focused on light sheet imaging techniques enabled by optical field engineering. So my talk will be basically two parts. So first is the background, very brief background for light sheet microscopy. And the second part will be the recent two works. One is published in Photonics Research, which is by using the point spread function engineering, we have developed isotropic 3D resolution light sheet imaging, which with very high spatial resolution. And within this content, basically, we recently developed a new one, which incorporated wavefront engineering with the first work. And it also shows very good performance. And at the last, I probably will give a very brief conclusion. So for light sheet microscope, so basically, this is a very brief introduction for light sheet imaging. So to optical physics scientists, actually, I think the scenario is very simple. Basically, people use two objective lenses. First, they use one lens to create a very thin sheet-like illumination optical field to excite, for example, the fluorescence imaging. And then we use another perpendicularly arranged objective lens to collect the excited fluorescence signal. So as you can see from the video, basically this technique is very interesting that we can do very fast 2D imaging by just take one shot from the direction of the detection objective lens. So comparing to the conventional wide field fluorescence imaging, like this figure shows, as you can see, if we conventionally focus a wide field light into some biological samples, and usually what we are looking at is a focal plane. However, if you look at the beam path, basically along the beam path, a lot of photons are wasted. So they create out of focus fluorescence light, which usually we don't need that in 3D wide field fluorescence imaging. And another thing drawback about this is all these wasted photons basically bring photo damage and phototoxicity to the biological samples. So with the light sheet, as just shown in last previous slide, basically, once we do this light sheet excitation, we concentrate all the photons at one plane, form a two-dimension sliced illumination plane, and then we detect this plane from the other side to collect all the photons, all the excited fluorescence photons from the illumination. So by using this method, as you can see, what I can say is I think the light sheet imaging basically is so far the most photon efficient technique, which we don't waste any photons, especially in the focal plane. So basically just like create a very thin sheet and to collect all the photons. So this is also, I think, is another advantage for light sheet microscope is basically what you have here is a virtually formed sheet-like illumination, and then as long as you control the thickness of the sheet, you have very good optical sectioning capability in light sheet imaging. As you can see, the difference from the wide field and between the wide field microscope and the light sheet microscope. So basically, we have a vertical cut of the sheet to slice through the 3D biological samples. So that's the basic running principle for light sheet fluorescence microscope. So to be focused on light sheet microscope, of course, I mean, there's one major performance we are looking at. For example, if you use a very low numerical aperture lens to form the light sheet, usually you will have very thick light sheet. That is to say, you will have worse optical sectioning capability in this light sheet excitation. And of course, for optics researcher, we can immediately think of why not we can use a high-NA lens to form a very thin light sheet. By doing this, basically, we can have a very high axial resolution. And the overall 3D resolution basically is determined by the overall imaging system, which here, as you can see, basically is determined by the two lenses. One is from the illumination lens, another one is from the detection lens. So for this scenario, basically, if we look into the 3D point spread function or the 3D resolution of such a light sheet, imaging system basically is a multiplication of this excitation and the detection. So that's the basic principle for determining the performance light sheet imaging system. And obviously, we now have certain trade-off and limitations for using a light sheet imaging system. As you can see from here, if we want to have a very good optical sectioning capability, then we need to use a very high-NA lens. And we know along the excitation axial direction, if you use a very high-NA lens, basically we will have shorter field of view for the side detection or perpendicular detection scenario. So there are several, limitations and the trade-offs in light sheet microscope. So I think first thing is trade-off between optical sectioning capability and the field of view. So if we want to have a very good axial direction or Z resolution, basically we will sacrifice over this field of view. And follow the first trade-off. Basically, I think it's also getting difficulty to get a uniform isotropic resolution in all three directions. Also, as you can see from the first introduction, with perpendicularly arranged two high-NA objective lens, basically the sample mounting is getting more complex. So with all this idea and basic background in mind, this field actually has been drawing attention for a long time, and there are a lot of new techniques, a lot of developed techniques based on the light sheet principle. For example, there are a lot of like this single lens light sheet microscope, also this diagonal selective plane illumination microscope. So today in this talk, we are particularly interested and focused on the reflected light sheet microscope. As you can see from all these diagrams, so basically the conventional light sheet looks like this. So you have two perpendicularly arranged objective lens, and that makes all the system, the alignment and the sample mounting, it's more strange, not that straightforward. And if you look at the reflection type light sheet microscope, basically it's pretty much similar to what we have in a traditional transmission type microscope. So what we are doing in today's talk, showing in this talk is we're focusing on this scenario. So for reflection type light sheet, there already have some previous developments from many excellent groups. They have doing this for years. For example, there's one example. People can use the single objective lens by using a reflected sample chamber with certain degree tilted angle, and they can excite this light sheet illumination from the side and detect by the single original the same lens. So this is a single objective lens plus reflection or reflective element. So in this scenario, I think the limitation is basically you cannot use the full numerical aperture of your lens. for both excitation and the detection that will, sacrifice somehow a little bit on this spatial resolution. Also, people can use more engineered idea. For example, people can use AFM cantilever, use the cantilever as a micron reflector in light sheet microscope, and they can build two objective lens head-to-head, like some situation in 4-pi microscope or in transmission type microscope. So they do this usually in they put all these reflector or reflective element in this excitation beam path to perform beam steering or point spread function engineering same way to do this in a reflective way. Also, people can use very miniature prisms to do this. The previous report has shown that people can use very tiny prism to reflect the light from the illumination, to bend the light from the one direction to the orthogonal directions to perform a reflective light street microscope. So all this previous work, I think they are focusing on how to bend the beam or how to modify the total point spread function in the illumination way. So, but as you can see, so previous work basically they all use very long working distance objective lens because they need to space to do the excitation. The long working distance usually will give you a lower NA. That means if you use very low NA, so you will sacrifice the thickness of your light sheet. So that's the first point. And the second point, I think here it is if you look at the scenario, basically you have a certain angle. For example, I think they both use 45-degree angles. So that means the excitation angle of your illumination system will be limited by this particularly reflective angle. So that means you cannot use very high NA lens to high NA capability to form a very thin light sheet illumination. So our method basically is not that tricky. So what we are thinking is why can't we just flip the scenario here instead of putting a reflective element in the illumination beam path? Why not we can do that in an opposite way? So by doing that, for example, here, we can use a very high NA excitation objective lens to form a very thin light sheet to establish the very good optical sectioning capability. And then in an opposite way, instead of we put this reflective element in the excitation beam path, we can put that into detection beam path because in this way we can avoid the limitation on excitation numerical aperture capability. So that today we can form a very thin light sheet excitation, and then we can use another high NA lens for the detection part. So this is a basic scenario. I think it's very simple and it's kind of engineered and it's very related with engineering idea. So here basically we can do some simulation on the system first. For example, we know the detection point spread function from the detecting objective lens, and then we know we can use high NA lens to form a very thin light sheet. So we can do a simulation by beam propagation method, and then we can combine them together to get a very good estimation on the overall point spread function or the spatial resolution of the system. So basically, based on our simulation, it's pretty good. It's around, I think it's around 200 nanometer. So depending on what kind of excitation of the lens we are using. So first, we try this idea with conventional Gaussian beam excitation. So we put a Gaussian beam in front of the excitation objective lens, and we can form a line of, and if you scan the beam by using beam steering method, for example, Gavo or another beam steering device, basically we can form when the scanning is very fast, we can form a light sheet. So in the detection part, we just do the conventional wide field detection. So this is what we can have with a Gaussian beam. And we found out that in this case, because we are using very high NA length, here we use, I think, at least 1.1 NA, which is water immersed length. So once we use high NA length, basically what we will have here is a very short light sheet in the axial direction from the excitation part. So and later on, we change the incident beam incoming beam to a base L beam, which is well known that we can have a much longer field of view based on the high NA objective length. So this is the basically this is the simulation and with the high NA length with the incident light of base L beam. So based on the simulation, we decided that we should go with the base L beam light sheet and with also with this reflective detection scenario. So this is what we have done in both simulation. For example, the first row is the simulation by using a NA of 1 water immersed lens for the excitation, and we use the very miniature reflecting prism, which the size about 1 millimeter in the detection part. So then we can use the identical objective length of is another water immersed lens to do the signal collection. And here is the first row is the simulation, and the second row is the experimental measurement of the system performance. So we use, basically we form the light field here, and then we use a very tiny, I think it's 100 nanometer or maybe 80 nanometer in golden nanoparticle as a probe to scan the field so you can see the field experimentally, which is agreeing with the simulation very well. And also we try a very extreme situation here. We also replace the excitation objective length to a 1.4 all immersed objective length. So as we can imagine that because now we are putting the reflective element in the detection part, so there's no limit for us to use any high NA length in the excitation beam path. So we try this with 1.4 NA length, and it's pretty good actually. With the base L beam, we can get much thinner light sheet imaging. However, in this work, the final result, we didn't use the 0.4 because we also want to bring the isotropic 3D resolution into the system. So if we use 1.4, basically the axial direction, the Z, the resolution in Z dimension will be much better than the transverse direction. So it depends on the application. So in the future, maybe we can switch to high NA length for the excitation, and we can get much thinner light sheet excitation. So then we build the experiment. As you can see, we use a very tiny prism as a reflective element and incorporate the prism into the sample chamber. And then if you look at the experiment briefly, we see this pretty much like a traditional transmission type microscope with 2 objective lens head-to-head, with which here we use 2 identical objective lens with NA of 1, which they both were water immersed lens. And then the other thing, the other part of the experiment is quite conventional. So we build a scan lens to fast scanning the beam that we can form a sheet, and then we can, by transmitting the sample, we can do the 3D imaging in a very fast way. So here is the measurement of the system performance. Basically, we use the very tiny fluorescence bead as our first calibration sample in the system, and we measure the system performance. And as you can see, we do this in transverse. type, and we also can measure this in axial direction. So the 3D resolution in these directions, they are very similar to each other. So then we can call this isotropic in 3D directions. And basically, we got close to 300 nanometer in both directions. In all the three directions, and we use the excitation light as wavelength is 561. So if we can use shorter wavelengths, then we can of course get a better resolution here. So I think the key point here is we can, using this scenario, get a very comfortable 3D isotropic resolved fluorescence imaging. So we try this on very big, for example, 10 micrometer fluorescence speed in 3 dimensions. So we can measure the 3-dimension profile of the particle samples. Also, we try this method technique with some biological samples. Here is an example of the experiment. We used Drosophila RH6 cells to test our system, and it got very good imaging quality. So in this biological sample image. So based on this, so this is pretty much the first work Professor Yang just introduced and published in Photonics Research. And as you can see from our experiment, so all the performance, basically we still, even when I talk about the comparison between the Gaussian beam and the basal beam, even with basal beam, so we still has a very limited field of view. So for in this case, we only get 7 to 8 micron in field of view in the null direction. So it's far, I think, behind the requirement for do real, imaging in biological samples. So what we are more focused on recently is, based on this work, we take another further step into the whole system that also, as I introduced, there is another trade-off between the thickness of the light sheet, because now we can use very high lens to do the excitation. So we will have very thin light sheet. However, that will limit our field of view. So this is this is a common trade-off between the optical system. So we were thinking how we can overcome this problem. So, and this is a general trade-off, general problem. So and we look at some scenarios. There is a newly developed scenario, a scheme, which called axially swept light sheet microscope. So basically, because the scenario behind this word is, if we cannot get a very large field of view at one time, so why not we can do the beam scanning or the light sheet scanning. So first we can form a very thin, however small field of view light sheet. However, if we can do the scanning of this small light sheet to stitch or the signal to a large field of view, at the same time, if we can, you can do this on your detecting camera, for example, by using rolling shutter to detect the moving or the scanning small field of view light sheet signal in time sequence, and then in a very fast way, and then you can stitch them together to get a very large field of view fluorescence image. So I think this is also a very straightforward idea. So the idea to do this is we need to first form a light sheet, and then if it's limited in field of view, then we should do the scanning of the light sheet. So that it's kind of like you scan the beam with a certain method. And we all know in this scenario, so the assumption is we should use very high NNS, because we need to generate a very thin light sheet by using high numeric aperture and optics in a system. So this is like the animation showing here. And the conventional way to do this is very straightforward. People can use and add on some phase modulation. For example, Tenure modulation, Tenure phase profile. And then basically it's just changing the divergence of the incoming beam, and then you can do the scanning after the high numerical objective lens. The one limitation or one drawback of this method, of this direct phase modulation method, is with a very high NA. That means you have very high focusing, very large focusing angle. Is that in the system, basically, if you just simply put a Tenure phase modulation in your system, that will create very bad aberration of your beam along the, in front of or behind your focal plane. So our method to overcome this problem is we want to borrow the idea from the computational optics community that why not we can just form closed loop calculation first to find what is the best, what is the optimized wavefront phase engineering distribution in order to form a very long scanning after the high NA lens. However, we don't want to create any aberration in this case. So the configuration is very simple because we know the spatial light modulator can do phase modulation. But what we can do is we can establish certain algorithm first, knowing the system's components, knowing the system's parameters, and then we can establish a kind of pre-calibrated mapping by using the computational framework. Here we use the GS algorithm to pre-generate a lot of phase modulation patterns in such a way that, as you can see from the upper diagram, so we can do this in a computational way by using the GS algorithm to form a very nice aberration-free tunable focal point or focused field along a very large field of view. Okay, so here is a simulation showing we can do this in 200 micrometer. In comparison to the conventional method, if we just simply use Tenure phase modulation, basically, as you can see, on the high NA excitation, we can see a lot of aberrations along the optical axis. So this is the essence of this work. I think it's not that fancy, but it works very well. Basically, we just use the GS algorithm, knowing the system's components, and we can, I think it's, sorry for that. I think something. Okay. So can you see my screen?
Yes.
Okay, sorry for that. So this is the basic idea. So, and then what we can do is just based on the previous work, actually just published this year. So we build another configuration, which we put a spatial light modulator into the system, and we can do the pre-calibration, and we generate a very large range of the scanning focal point to do the to generate a light sheet. So the hardware basically is pretty much the same of the previous one, and instead of we add on a phase modulation from engineering capability, and of course in doing this a little bit difference for previous work is previously we only have a fixed range of field of view, and now we can do this in a very large range of field of view. So we need to put an electrical tunable lens into the system to tune the focusing detection for the detection part. So that's the basic the idea. And this work is almost finished, and we still is in review, and we got some feedback, and we are working on some improvement on the current work. So with this in mind, what we do is you can see the difference. If we just if we don't use this wavefront engineering method, basically what we can do is we can use a high energy lens to do the light sheet excitation illumination field. However, in a very short of range of field of view. So previously we only can generate like 10 micron. And then with this wavefront engineering method, by preloading all this phase diagram into the spatial light modulator, what we can do is we can use a very fast spatial light modulator. So then we can do this scanning in a 4K, 4,000 hertz speed. So we can get a very large field of view around 80 micron. And at the same time, because we use this reflective type configuration as previous work, same as the previous work, so we're still getting a very good isotropic 3D resolution in the system. So as you can see, we test the performance of the system, which all direction gives us about 280 nanometer in spatial resolution. However, comparing to previous one, we only have 10 micron or 8 to 10 micron field of view, and now we can have 8 times better than the previous one. So we do the more system calibration, like we scan the beam, and as you can see, the beam line, the line to be formed as the light sheet is very uniform. And also we try this idea on some zebrafish biological samples and get a very good result. So I think this work is closely related with the previous one. So today, so that's why I'm just adding this unpublished work into this talk to show you what is the potential capability to do this. Okay, I think with a very brief conclusion, I think this at the initial we didn't think that this reflection type hardware configuration will work so well, but after doing experiment, we found the performance actually is not bad. Even we don't put very breaking through idea into this scenario. However, even we just switch the beam path put the reflective element into a different beam path, that we can generate a kind of framework that we can further working on the field engineering method to improve the whole system's performance. So I think in the future, we're still working on this framework and see if we can get much better performance in field of view, in both field of view and spatial resolution. And this work is mainly done by my student, Yue Wang, and she's graduating this year. And also I want to thank the funding agent from PNAS China and the MOST. So with that, I want to thank you all for the attention, and I'm happy to take questions. Thank you.
Thank you, Kebin. Thank you for this insightful discussion. I do have some question for you. This is very educational. So what is the major difference between your approach with others that has been reported by other groups?
I think the major difference is I think we first proposed to put this regarding the reflective type light sheet microscope. I think the new thing here is we just switch. We switch the way people putting this reflective element into the optical system. I think because we are more focused on to get very good optical sectioning capability. So that means we need to we don't want to have any limitation on the excitation numerical aperture. So that's why we put the reflective element into the detection part. It looks like a small step, but we found out that is quite interesting that we can get very good performance on this idea. So I think that's the major difference.
Okay, and then what's the limiting factors for your system performance?
Oh well, I think if we could go to the system, here. So the limiting factor basically the same with the previous one. Previous one, they use this reflective element into the illumination path. So then that means the illumination numerical aperture is limited. So here in our system, as you can see, so because we use this miniature reflector in the detection part. So for example, assuming this is a 45 degree, and we can do the calculation. Basically, consider the medium reflective index like 0.3 if it's water. So basically, with the angle of 45 degree, that means the detection NA is also limited in our system. So we cannot get very high NA capability in the detection part. So in this case, if you do the calculation, consider the 1.3 medium reflective index. The NA is about 0.9. That's the upper limit for the detection part. So that's why if you look at the resolution part, this is limited with the detection part, basically not the axial part. So well, I think this arguing point. People can argue with us on that. So yeah.
Okay.
Yeah, but in the future, yeah.
In the future, what?
In the future, if we use, well, if we don't really care about the isotropic resolution, I think what we can do is, we can use very high NA excitation, which get a much thinner light sheet, and that means, regarding the detection part, we get a very good the Z direction resolution. However, the transverse one will be probably worse than the actual direction. Yeah.
Okay. Can we stay on this slide? Actually, we started to get a question from the online attendees. The first question is, how are the samples placed in this case?
Oh, that's good. Very good question. So that will really, well, if you look at the chamber of the sample, so I think this is also another drawback for our method, because we need to have a customer designed chamber to put all this minimum this miniature prism into the system. So we kind of customize the chamber, and according to my collaborators in the biomedical side, so they don't like the chamber because if we want to culture live cells in the culture, so in the system, so this chamber apparently is not very compatible to traditional or conventional life science culturing system. So I think that's the thing we need to improve in the future. So what we do is kind of like rectangular slot here in this way, and yeah. So and we can put sample inside of the chamber.
Okay.
It's open top. Yeah.
So is it easy to handle live samples?
In this particular case, we haven't tried live samples. I don't think it's. I don't think my collaborators or students in the biomedical collaborators, they probably don't like this chamber, especially for culturing the life cell. But I think I think it's not a fundamental limitation. It's related with some probably practical practice in this case. Yeah, I think it's durable, but maybe need to put some effort for my collaborators in biomedical side to work on this system. Yeah.
Okay, so with that in mind, can you comment on the future development on this current approach?
I think because light sheet microscope actually has a lot of applications. So one thing is they want to have, usually, I mean, the field, I think people want to have a very large field of view and very good, highly spatial and temporal resolution. So regarding our method, I think the idea here is we can probably incorporate the system with, for example, the microfluidics system by customize some spatial chamber and do this, use this technique, particularly for some specific application. Yeah. So to be honest, I don't have any, so far, I don't have any very thought out idea on what kind of application this technique will be, but we're working on it.
Thanks. Okay, now our audience became really active. There's more questions coming in now.
Okay.
So next question is this system compatible with Palm or Storm super resolution?
Oh, yes, I think it is, yeah.
Okay, so you can modify your system to be compatible with others, right?
Oh, yes, because I think I have the whole picture for the system. Yeah, so if you look at the, let me take a look. Okay, here. So if you look at the arrangement of the sample part, so basically it's pretty much like conventional microscope. So these two objective lens, they are, so these two lenses, they are in kind of, they almost, head to head, because we have a reflective element over here. So they are a little bit displaced along one direction, but I think it's compatible with any fluorescence or not any, so we can modify this, or we can probably do some Raman storm experiment on this system. I think that's doable.
Okay, and so next question: what is the base angle of the icon? So how will the factor?
I didn't hear you clearly. Can you repeat?
So will results.
Okay.
So what is the base angle of the hexagon? So this is a specialized type of lens, which is a conical surface. So they wonder about the special lens in the cell.
No, we don't. I didn't hear you very clearly. So the question is, do we need any special designed lens for the excitation?
Yeah.
Okay.
Yeah.
Oh, no, we don't need to have any special design. So for the generation of bezel beam, it's just a very conventional. I'm not sure if it's here. So we just put off the shelf, from, I think it's from Solabs or maybe some Chinese company.
Oh, this is hexagon. Hey, Kebin, there's an hexagon lens here, right? I think he or she probably wonder about angle, the base angle of the hexagon lens. Because it depends on the curvature.
Right. Depending on the apex angle. The scanning. Good question. I forgot the detail. Maybe you can check on my paper.
So
sorry for that. I forgot what is the apex angle. Maybe I think it's around the 176 or 174. The apex angle, probably, yeah.
Okay. How will that affect the results if you choose a different, for example, curvature, the angle? How will that affect performance? How do you decide how this is the kind of angle I want to choose?
That's the question. So, depending on I think we did the Zmax simulation. The Zmax one is kind of a numerical one. So depending on what is the, for example, excitation NA we are using for here is NA is 1 for the immersed, and I think we did some simulation on that to test on the performance of the system, to to determine what kind of apex angle we should use. But in the end, I think the major limiting factor here is the NA of the objective lens that will limit the field of view of the generated field of view of the light sheet along this direction, as you can see from here. So yeah, I think we try different strategy. I think the best we can have right now for this scenario without any wavefront engineering is around 8 to 10 micron along the kind of field of view length.
Yeah. Okay. I want to ask you a few questions for students. So, innovation and creative research is at the heart of research, right? Especially for young researchers. So here in this work, it seems like this miniaturized prism is the key innovation, right? And it's a very simple idea compared with the sophisticated system. How did you come up with this idea?
Oh, well, yeah, I think we initially I thought this is a very, very, very simple and small project because my PhD student, Yue, she had the experience for optical taser project. So to me, this work started as a practicing project. As you know, first year student, I say, okay, so since you already have the experience on optical tailoring system, what my student previously did is they used this lower objective lens to perform a optical taser capability along the axial direction. And what they need to do is they need to, in their previous work, they need to show people that they really did this in axial direction, right? So for taser, people usually use one objective lens for both manipulating and observing of the tracking particles. However, in this case, the particles are along the axial direction, and they don't have any capability to do this. So what they did is they put the prism over there for the side detection, for the side imaging. So yeah, I think based on this idea, and I signed this initially I thought it's a very small project to her, and I said, okay, so why not we can try this optical trapping idea, migrate this idea to light sheet imaging system. Since we did little research, nobody has done this, so I said, why not we just try this? And I think it turns out very well in the initial performance. And then based on the first work, as you mentioned, already published, we find this is very pretty interesting actually. Just by simply flipping switching the detection, the direction of putting the reflective element, we can actually do more. So that's how the story, evolved in this case.
So innovation is driven by needs, right? In this case.
Yeah, driven by needs or building upon the previous, work. I think that's always my starting point. I also search for what people have done. Okay,
build on your past accomplishment.
Right, and what we need to do better, better way, and then we figure out what kind of methodology we can use.
Yeah. So I bet some of the attendees are not in the field of microscopy. So can you summarize, for example, or give us a take-home message about what is new capability or functionalities enabled by this miniaturized prism added to the system?
Well, I think the first advantage for using such a method is making the whole system is more like conventional microscope instead of perpendicular range to objective lens. So I think that's, to me, probably that's the major advantage by first glance at the system. So of course we need to improve as there's all in question that as you can see right now the sample chamber or the holder is not very compatible to the conventional life science research. So, but I think we can have a method to work on that. I think so. This is probably the first. Well, I think it's more practical orientated advantage for our method. And I think the second advantage for our system is based on the basic hardware configuration. I think we can add on more computational method, like the second work I just introduced, to enable the system with much better performance. And we also got some new ideas on the system. We're still working on that in the experiment. So hopefully we can, share with you in the future very soon.
Sounds
that's
great.
Basically.
The last question. Powerful technical tools. You comment on the impact of the tools. You did mention 0% what is other cases and other views that
sorry, I'm not sure if it's my network problem. I didn't hear the question clearly.
Yeah, let me repeat my question. So let me give you some examples that using the tools or something better tool.
Yeah, I still don't get it. Sorry. Yeah, it's kind of interrupted.
Let me stop the video.
Yeah, maybe just wait for a few seconds. I'm not sure which side of the network is getting worse. So can you try it again? Yeah.
Okay. Can you hear me now?
Yeah, I can hear you.
Okay. So the last question is, you did showcase some examples such as zebrafish that can benefit from the tool, the microscopy developed in this study. Can you comment on other fields or interesting problems that can make best use of the tools developed in this work?
Yeah, well, that's a tough question for me because I'm actually not that into biomedical applications. So I think in the future, once we basically we are working on the third project based on this scenario, so we can get now a much larger field of view with still very good visual resolution. With that capability, I think we can do much larger scale 3D imaging in a very fast speed. For example, we can look into brain slides. Actually, I'm working with some scientists here in Beijing, and we want to actually expand the capability of the system to get a large field of view with similar resolution as these two works. So then we can, I think, we can do much larger scale 3D imaging with high resolution in 3D. So that will be a technical advantage for us to find more interesting applications. But really, it's a tougher question for me because I need to have a lot of discussion with my collaborators in the biomedical side.
Yeah. Okay, now time is up. We need to conclude our webinar. And now I want to take the chance to thank our speaker for sharing his insight and the vision in light sheet microscopy with us, and not only with us about the technical innovation to achieving isotopic 3D resolution, but providing impact with technology. In addition of about science, I do appreciate the way he treated the questions. I think it's insightful also for students. For example, when I asked him about the impact of other fields, he truly gave me the honest opinion about his lack of knowledge about medical research. But I think that's truly normal, and that is why we need to publish our work so that other people around the world will be able to see that. I have no doubt about there's a broad application and the impact of this discovery that really will become a very powerful tool to unravel a lot of interesting phenomena in biological samples. That is the element of research. And as I said, when I give a talk, I said, what is research? If you look at the word research, right? Search and search again. Read means do it again. So research means we search and search again. And as Professor Shi mentioned, although currently is not aware of the application, but once the paper is published, people are aware of his work. Maybe there are more people in other fields will reach out to him. I truly wish him the best luck to find a powerful application for his tools and that showcase today. And in addition to give my gratitude and appreciation to Professor Kebin Shi, I also wanted to thank you who are sitting here and joining the webinar from all around the world. I look forward to welcoming you to our future webinar where we can continue to explore and groundbreaking discoveries together. And so thank you once again for time and engagement. And I wish you a wonderful day or evening wherever you are.
Thank you, Professor Yang.
Thank you.